How about simultaneous games in oligopolistic markets? Let's start with simultaneous output setting, which is known under the name of Cournot model. So buyers set the price and producers would adjust their output to the price. That is the assumption of Cournot model. And one firm set their output under the assumption that the rival's output stays the same. So my decision is based on the idea that probably the decision of my rival wouldn't change. And last, the most problematic assumption for this model would be costless production, or at least without differences in costs, and zero marginal cost, which would mean unlimited supply. That was the original version of Cournot model. Nowadays, we know how to modify it, how to get rid of this last assumption. Because this last assumption is pretty problematic. I mean, how can you expect that marginal cost could be zero? It's very difficult to find such a situation. Whenever you want to produce one, you need more of something. This is cost that is greater than zero. Obviously, we can find some cases like, for instance, digital products. Okay, so if one person more watches your movie clip on YouTube, then actually it doesn't create a lot of marginal cost. In the times of Cournot, and this is 19th century, the only quite reasonable market that could be analyzed with this assumption of zero marginal cost was the market of mineral water suppliers. Because if you produce mineral water, if you make the well, this professional industrial well, then getting one more liter of water, it really costs you close to nothing. So you can assume this is like zero marginal cost. Okay, let's have a look at the Cournot model, what it looks like. So we've got our slide here with quantity and prices and demand. This demand would be called D1. D1 because we need to start somewhere this simultaneous game. And let's start this game by a certain assumption. Our assumption is the player number 2, it's not the follower anymore, remember. The player number 2 produces 0, doesn't produce at all. So we will see what would it mean for the first player, and then we will move back to the second player. At the very beginning, the second player produces 0, produces nothing. So the whole market demand actually belongs to the first player. If this whole demand belongs to the first player, then this player can be seen as a kind of monopolist. So we've got this D1, we've got our monopolist that uses marginal revenue to find the production. And remember, marginal cost was 0, so the marginal cost is actually on this horizontal axis. So this point of intersection is in the middle between 0 and 960. So this is 480, and this is the production of the first produce, right? And then the demand function is used to find the price. So for this quantity produced, that would be the price. We call it P1. So if the first player acts like the monopolist, and this is due to our assumption, player number 2 does not produce anything, okay? Then the solution looks like that. If the second one doesn't produce anything, then the first one would produce 480 and would sell at the price of P1. Now, let's move back to the second player. If the first one produces 480 and sells at P1, so how much is left for our player number 2? And we look at this problem, how much is left for the second player, just like we did with residual demand. So let's consider two levels of prices. If the second one wanted to sell at price P1, then at price P1 people are willing to buy 480, and this 480 is already sold by the first player. So for the second player, there is zero of free space in the market at P1 price. The second point that we can try to investigate is what would it be if the second player wants to sell the product at zero price? Well, at zero price, the capacity of market is 960, but 480 is already sold. So what is left for the second producer would be the remaining 480. So for the price P1, there is nothing for the second producer. For the price of zero, there is 480 left for this producer. So we draw the D2 curve, and this D2 curve is like residual demand in the model that we learned. So this is the demand for the product of the second producer. And within this D2 curve, our second producer may act as a monopolist, who's the only one to satisfy this demand. Therefore, we will have the marginal revenue here, the point of intersection with marginal cost, which is on the horizontal axis. So that would be 240, and this is the production of the second producer. What would be the price? Well, the price will be taken from the demand function. This is the price P2. And this is the first phase of our model. So look again, our first assumption. The second player doesn't produce anything. So Q2 is 0. If Q2 is 0, then Q1 is 480. But then, if Q1 is 480, then Q2 is not 0 anymore. It would be 240. If Q2 is 240, then what would be Q1? It wouldn't be 480 anymore, because 480 offered by the first player was the best solution, was optimal, if the second one doesn't produce anything. But we know they would produce 240. So actually, the first player needs to reconsider the situation and calculate once more how much they would produce. But obviously, if they change their production, if that is not longer 480, this change in their decision of the first player would also influence the decision of the second one, because the second one produces 240 only because the first one would produce 480. If that's not 480, then 240 is also not the actual production of the second one. So as you can see, the first one produces in response to the production of the second one, and the second one produces in response to the production of the first one. So they are reaction functions, and we know them here. You can put the numbers, like for the first equation, put 0 instead of Q2, and this block capital Q is, as you know, the capacity of the market, so that's 960. So if Q2 is 0, then Q1 is really 480. Look at the second equation. If you put 480 instead of Q1, then Q2 would be 240. Now take 240, put it to the first equation, and you get the new response of the first player, and so on and so forth. Is it endless? Can we come to some point? Yes, we can. We will find it, this point we will find quite easily if we skip this kind of coordinate system with P and Q for the whole market, and instead of that, we will use the coordinate system that is based on reaction functions. Have a look at this slide. So we've got functions of reactions. This is Q1 and Q2. This is the reaction of the first player to the production of the second one. Right? So we've got 960 here and 480 here. And we've got a similar, quite the same, reaction function of the second one with 960 here and 480 here. So let's start from the very beginning with the quantity produced by the second player equals 0. So Q2 is 0, then Q1 is 480. If the first one produces 480, then the second one would respond. And the response is the second one would produce 240. If the second one produces 240, then we look for the response of the first player, and the first player would change the production from 480 to 360. So the second one would also react to this change and would change their production. You can see that we're actually trying to move in some stairs, smaller and smaller stairs between the first and the second reaction function. And actually there is a point of intersection here. And in this point of intersection we will have our equilibrium, meaning if both producers would set their production at 320, then this is the equilibrium situation. If I produce 320, he would produce 320. If he produces 320, I will produce 320. So this is the best situation for me, taking into account his situation, and this is the best situation for him, taking into account my decisions, how much to produce. So in this equilibrium point, we have no incentives to change anything. I will keep on producing 320 because it is the best solution to me if he also produces 320. He wouldn't change his production because his production is the best one to him if I produce 320. So no one has any incentive to change anything because in the current circumstances, this change would be only for worse. The simultaneous price setting is known under the name of Bertrand model, and we can easily understand that when we look at public procurements, when public institutions try to buy something. So let's imagine, for instance, that the university wants to buy a huge number of pens and pencils, okay, for the staff, for the students. So let's assume that the university wants to buy 10,000 of pens and they want to buy it with reasonable price. Imagine that there are 3 possible sellers, and simultaneous price setting would be the situation when the university says, all right, we want to buy 10,000 pens, so each of you, our potential sellers, may actually prepare an offer right? You prepare an offer, you propose as the price. You put this price in the envelope and you send to us. And at a given moment, we will open all three envelopes, and the one who gives us the best price would win, others would lose. So this is open tender situation, right? And for such an open tender, we need to think of what could be the offers of those three businesses, those three sellers. Each of them wants to win the open tender, so they would propose really low prices, the lowest they can, because if they propose a higher price, they would lose against the competitor. So what is the possible lowest prices? The lowest possible price for any business is the price that is equal to marginal cost, like in perfect competition. So if they want to win, they would propose the prices that are equal to their marginal cost. And the person, the business that has the lowest marginal cost would win this open tender. As you can see, this is a very powerful tool because obviously you have only three sellers or even two, not many of them. So this is a situation very close to the monopoly, yet it allows you to get the result that is a typical result for perfect competition, right? Where there are many, many, many competitors, okay? So we kind of introduce this level of competition among two, three, a few players with the simultaneous price setting. Obviously, there are some problems regarding the question of honesty because, well, if they cooperate while proposing their prices, then obviously this open tender wouldn't be that efficient. And obviously, for open tenders, public procurements, generally speaking, maintaining the quality is pretty problematic. Because in open tender, it is easy to say, all right, the cheapest offer win. But actually, it's not only about being the cheapest, but also quality is important. But this is quite difficult to measure quality, right? And there are some problems regarding that.